Hi everyone, my name is Nick Karpowitz and I'm a physicist at the Max Planck Institute of Quantum Optics, and I wrote a bit of nonlinear optics software that I've released into the world called Lightwave Explorer. And in this video slash series of videos, I wanted to give an overview of how to use it and the sort of things that you can do with this code. So let's start with our guided tour. First, what is Lightwave Explorer? It's a nonlinear optics simulation, which means that what it's really designed to do is take some light field and see how this light field evolves as it interacts with a nonlinear optical system, such as a nonlinear crystal or system of optics around a nonlinear crystal. Key parts of this code are that it's open source. Since it is scientific code, I think it's important that people are able to look inside and see what is producing these results. It's multi-platform, so you can run it on Windows, Linux, or Mac, and it is heterogeneous, by which I mean the same code can run on a GPU, graphics card, or a CPU. The short version is that it gets compiled by 3 different compilers: NVIDIA's CUDA compiler to run on NVIDIA graphics cards, Intel's DPC++ compiler to compile it using the SYCL language, which at the moment allows it to run on Intel GPUs, but in the future should also allow it to run on AMD GPUs, and it will run on a CPU using the base language of C++. Designed to be fast, so numerically should be efficient, which is important if you want to study complicated systems, but at the same time friendly. So it has a graphical user interface and it's very visual. So when you're interacting with your system and adjusting your light parameters, your crystal parameters, it has a lot of visual feedback, which for someone like me is very important for understanding how a system actually works. It's designed to allow you to construct multi-element sequences, so not just interaction with the single nonlinear crystal, but with a more complicated system. And I want it to be extensible and testable by the rest of the community. I don't just give you a set of crystals that you have to work with. If you have some sort of interesting solid state system in mind that you want to work with, it is not too hard to add crystals to it. It's in a human readable database, and I want it to be testable by the community as well. Really, like in a lot of things that we do in physics, we're solving a set of coupled nonlinear differential equations. And solving a partial differential equation like this means typically you're taking some initial state of your system, which is the electromagnetic field, and seeing how this propagates over time as it interacts with this environment. In this case, that's seeing how a laser pulse or series of laser pulses will evolve and interact as they move through a nonlinear system. And that system that you simulate can be a single element. Say you just want to look at effects happening inside of a nonlinear crystal, or it can be a whole laser cavity, something more complicated with multiple focusing mirrors and optics and free space propagation intermingled with the nonlinear elements. And once you've set this up, you have your numerical result, and you've compared it against an experimental observable that you have access to, which is sufficiently detailed to judge these kinds of things. It allows you to look inside and look at the inner life of the light fields as they're moving inside of your crystal. And in the end, you can compare these results versus various experimental observables, not just for understanding your own system, but to better estimate the physical properties of the system that you're working with. So how do you do this? To start, you're going to need the code, right? So this is located on GitHub. Here we are on the GitHub website. And if you're not familiar with how GitHub is organized, at the top of the site for my repository, first thing you'll see is a list of all of the source files. We're not going to really go into that today, so what we'll do next is scroll right down to installation on a Windows PC, because this is a Windows PC and that's how we're we're going to install it. If you click on this link, it will bring you to this shared volume where I just keep the compiled versions of the code. You can just pick one of these files. The 7-zip and zip are the same stuff, or same contents, just a different compression format. So we'll use 7-zip because it's a little bit more efficient. So we can just open that, extract, and now we have our Lightwave Explorer folder. You can put this anywhere you want. Typical is program files, but it'll run anywhere. So we can just launch the program. It'll start here. And here is our user interface. So if you see on the left-hand side, there's 2 columns of numbers, quite a lot of numbers. And these are all parameters describing an ultra-fast laser pulse. By default, you can interact 2 of them inside of your nonlinear medium, and we have some ways to introduce more if you need them. But just to start with, we're going to look at some simulations that just need 1 or 2 pulses. The default values that are in here are just some typical pulse parameters for chromium zinc sulfide laser. There are quite a lot of them. They're all describing a synthetic pulse, by which I mean pulse is just generated analytically using these pulse parameters. If you want to, or if you have data available, what you can also do is load in data in various formats, such as frog, frequency, result, obstacle, gating, to give you a more close to experiment input pulse. But for what we want to look at now, a synthetic one is good enough. So this is just describing the spatial and temporal parameters of the pulse. And then over on the right here, we have our properties of our nonlinear medium. In this case, you can see it's titanium dioxide. So for a typical nonlinear crystal, 2 very important parameters are the angles which describe the cut of the crystal, which is typically going to determine phase matching. The process that we're going to look at here doesn't care about that. They're both 0, just meaning that it's incident along the z-axis. Then we have 4 parameters describing the generation and motion of electrons inside of a laser-induced plasma. You don't really have to care about that for now. It's in this default calculation, but most of the time when you're using a nonlinear crystal, you don't want to make a plasma inside anyway, and then this absorption parameter would be 0. Below that, we have the parameters of our grid. So we have our spatial parameters, so how big our grid is in space. You can see just by default, it's 192 microns with a 0.5 micron resolution. And our time axis is also quantized here. So we're giving it a range of 320 femtoseconds with a resolution of 1 femtosecond. And then what the simulation is going to do, this is a simple simulation, just transmitting through 1 crystal, and that is going to be a 500 micron thick plate. And the parameter here is the step size of the simulation. So how large a single step of advancement of this grid is going to be. And this one, you just need to check that if you make it smaller, you get the same result so that your result is converged. So for this simulation, 1 micron is good enough. That is our spatial and temporal grid. And below that, we have our propagation method. Here, by default, it's assuming 3D coordinates, but assuming radial symmetry of the beam, because it's a single pulse sort of focused on axis. So radial symmetry is a good approximation for that. We could also put it into 2D Cartesian coordinates. So allow it to, say, have an angle relative to the axis, but don't allow it to diffract in the vertical dimension. Or we can do full 3D calculations to include everything. And you'll see below that there are 2 other modes called FTTD, which are using a more complicated propagation scheme where Maxwell's equations are solved on a spatial grid and propagated forward in time. But for now, we'll stick with this, the default. And if we hit run, we can just run the simulation with our default parameters. You can see it just takes half a second or so to produce the results of, in this case, spectral broadening inside of a titanium dioxide plate, which I'll show some pictures from the paper on the screen so you can see what's going on. This is one of the published cases where we actually used this code. All right, and so below that, you'll see two other things. So there are these batch mode 2. And what this allows you to do is to take some parameter of the simulation and do a whole bunch of simulations varying this parameter. For example, we can let's change the polarization of our pulse, or the circularity of our pulse. So this circularity 1, it started at 0. It's a linearly polarized pulse, which is why if you look here where it's showing the two waveforms on the EX field, it has a waveform here, and the EY, it's 0 because it's linearly polarized. Same story with the spectrum to the right here. This plot is a plot of the spectrum on the x-axis. This is a spectrum on the y-axis. And above that, you see the spatiotemporal distribution of the electric field. And to the right is its Fourier transform. So frequency versus k, which is kind of telling you the spectrum and spatial dispersion of light. All right, so we can run a batch mode. What we'll do is we'll take this circularity parameter and go from 0 to 1, which is going to go from linear polarization into circular polarization. And we can do this in, for example, 8 steps. And you'll see all of the newly performed simulations show up as they're done. And as you would expect, now we have a waveform on both axes. And what we can do is we can grab this slider and scroll through all of these various results, which is good for getting a feeling for how these things evolve relative to a given parameter. And these are things that you can mostly adjust in the lab. So these are things that are relevant for getting a feeling for. And if we want to take a closer look at one of these spectra, we have some controls for how the things are plotted. If we want to say look on a log scale to see more of the detail on the weaker parts of the spectrum, we can do that just by clicking that button. And on a log scale, it's often important to manually set your limits for your x and y axes. So let's do that. So our maximum is going to be about, let's do 3 times 10 to the minus 10 joules per terahertz, and our 13. Yeah. so we can see the important parts. All right, and we can also do the same thing for the x-axis, go from 50 to, let's say, 300 terahertz, just to zoom in our plots to give us a better look. We can overlay the total spectrum on top of that if we want to see how that changes. And yeah, as you would expect, the circularly polarized light is split about 50-50 between the two polarization axes. And once we hit linear polarization, or even close to linear polarization, most of the light is on the x-axis in this case. So that works how you'd expect, and this is solving a real case of some interesting nonlinear propagation, which you can read about in that paper. That first example, we were just running the default parameters of the simulation, but now let's try plugging in something else and to see like what kinds of things you had to change in order to make a reasonable simulation. I think a nice example is second harmonic generation in the BBO crystal. This is a very common thing that you would do in an ultra-fast lab. So let's just take BBO as our nonlinear medium. Like I said before, normally we're not making a nonlinear plasma inside of our linear crystals, so we can just set this nonlinear absorption to 0. And now we will deal with second harmonic generation in a BBO. So let's deal with a more standard case of, say, 800 nanometer light. Maybe let's make it a bit broadband, 50 terahertz of bandwidth, making a pretty short pulse. And we can, say, use a smaller time grid, but a larger spot size. 50 microns is kind of typical. We'll just put the crystal right in the focus by setting this Z offset to 0. And now let's choose better grid parameters. So if we're making a beam waste of about 50 microns, typically you want your grid size to be about 10 times that. And I usually do things in powers of 2 because there are a lot of Fourier transforms going on. So that's why I picked 512 microns there. And I think about a 4 micron resolution is going to be good enough. This pulse is pretty short, so we don't need a very long grid. Maybe 192 is good, but we will want a smaller step size, so like, I don't know, 0.4. And typically when I'm setting up a new simulation, I'll do it with 0 crystal length just to make sure that my pulse parameters look reasonable. Let me clear out my manual limits. All right. And right, we don't want polarization or a patch scan. So let's just send in linearly polarized light into our BBO crystal. So this is our input pulse. See, it's our input pulse because I just made the crystal length 0. One last step for doing phase matching in a BBO crystal is it has to go on the slow axis, which in this case is going to be the y axis in our polarization, and we have to set up our phase matching angles, which for BBO happens to be 29.2 with a phi of 30 degrees for BBO crystal, and this would be our grid. So we are sending in our light primarily here on the ordinary axis of the light, and we're going to make our second harmonic generation on the fast axis. So let's give it a appreciable thickness, and I'll make that a little bit smaller just to be safe. And we can send our light through it and make some decent amount of second harmonic. So you can see our laser pulse is going to be shorter than the second harmonic, which is showing up on the fast axis of the light. And that's because even though this process is phase matched, you can see there's this nice sharp peak there. It is not group velocity matched. So our pulse gets stretched out a bit in time, and you can see the second harmonic is kind of trailing the input 800 nanometer light because it has a slower group velocity. And the way this shows up in the spectral domain is you can see it more clearly on a log scale. There are these fringes where your light doesn't build up coherently, and you have these minima in the buildup of your nonlinear spectrum. If you were to make this, say, longer, 200 micron thick, you'd see that peak is going to narrow even more, and your second harmonic pulse is going to get even longer. You do convert more spectral amplitude in the center, but the amount of spectral amplitude that you get is more and more confined. So here's a decent view of second harmonic generation in a BBO crystal, and we can wonder, well, what are the effects of this assumption that I've made of radial symmetry, which was a good approximation for titanium dioxide, where we were moving in a direction along the crystal where the light wasn't experiencing much birefringence, but of course we are using birefringence to phase match, and well, that probably has some effect. So first let's just take a look in 2D Cartesian, because we're not so much concerned about the effects of diffraction, which obviously a 2D model isn't going to do, but it will get this effect of walk-off inside of the crystal. So if we now run this, we can see there is a little bit of a difference there. You can see that this second harmonic is a little bit tilted, and also in the K space, you see it's a little bit tilted. So this pulse front of the second harmonic got a little bit tilted here. If I go back to 3D radial symmetry, you can see the difference. And this is what you're going to miss if you assume radial symmetry inside of a birefringent system. Sometimes if you have spatial walk-off, that assumption of radial symmetry is a bad one, because especially if you're interested in what are the spatiotemporal properties of this second harmonic pulse that I emit, you have to get that kind of stuff right. So choosing the right propagation mode it's mostly a matter of understanding your system. And if you're really interested in all of the details of this, you would have to run the 3D simulation like this. And you can see it's noticeably slower, but still tolerable. And you can see the result is almost identical to what you got out of the 2D Cartesian, because the effect of diffraction in this case was not so strong. It's a fairly large spot size. But if you want to get all of these details right, that's when you run the 3D simulation. But this sort of pattern that I was using, where I set up the simulation in a 2D mode, and then once I was satisfied that this is describing my system, then I can switch to the 3D and then run the simulation from there. And then I will get the more reliable 3D result where I can really trust the spatially integrated spectrum. And when it saves the data, and it will save the data to, I mean, in this case, it's just default output/test file, this thing which I will just keep overwriting unless I put something special in this path. If I were to load this data, I would have this full 3D matrix describing the electric field versus time and space. So that gives you a nice, fairly complete representation of second harmonic generation inside of a BBO crystal. One of those very common things that you might do in a lab. Like, these are very reasonable parameters. Like this, like I would probably use more pulse energy. Like if I was up converting something like I don't know, a higher intensity such that it gets to this saturation point, and you can see it's starting to saturate the second harmonic. If you can look at the plot of the spectrum, you can see it's sort of carving out a little hole in the fundamental spectrum. In space, it's carving out a little hole, so it's quite intense at this point. But converting, you can see here most of the light into, because that's maybe a quarter is left unconverted of the light. So it's quite high conversion efficiency. You can see your spatio temporal effects are getting even more weird at this point. Once you enter the saturation regime, you can see these beams are very much not described by Gaussian pulses anymore. And this is a very simple nonlinear process that's going on, right? So this is stuff that's in the drawer of almost any ultra-fast lab. 800 nanometer pulse and 200 micron thick BBO crystal. And you can see there's already some fancy spatiotemporal stuff going on that if you really want to understand everything, you have to run a full 3D simulation in order to get this full spatiotemporal structure. And you can see even in this case, there's very little difference between the 3D and 2D simulation. So like the 2D will give you a very good starting point, and if your computer is slow, that's comforting to know. Okay, so that was second harmonic generation. Now let's go on to our next example. How to set up a optical parametric amplifier. This is a very common thing people like to do with nonlinear optics these days, and I'll base it loosely on the paper that my group did some time ago, where we're using a few different crystals stuck together back to back in order to get a nicer spectrum out of our amplifier. And it's a nice way to show this sequence mode of Lightwave Explorer. So now let's put in the parameters of our laser pulses. So I'll start with a fairly strong pulse, so 10 millijoules of light at 1030 nanometers, about 1030 nanometers, but very narrowband. So this is what comes out of a terbium YAG amplifier. Actually, in reality, it would be even narrower than that, but I just want to put in some nice numbers for the example. And now what we'll do is, obviously this is a bit too much energy to focus into a 11 micron spot, so let's do something more reasonable for a spot size of an OPA, which would be about 1.7 microns in this case. And we'll just put it also again right on the crystal. And our amplifier, as we'll set it up, it will be also in BBO crystal. And we also do not need any nonlinear absorption. When this parameter is 0, none of these matter, so you don't have to bother with those. But we will bother with setting up our grid properly. So we'll need a fairly large spatial grid at this point. So you can see I have a big spot size, so I'm going to use about an 8 millimeter grid with fairly coarse spacing, but good enough for a demo simulation. I'll give picosecond for my time grid, use a half a femtosecond step should be good enough for what I want to show. And for setting up our test calculation, I'll first start with a fairly thin crystal, and we will do it again in 2D Cartesian mode. An amplifier isn't an amplifier unless it's amplifying something, so we need a seed pulse for our amplifier. So we'll put in something at 2 micron with a healthy amount of bandwidth to amplify, and I'll give it a nice flat top shape just by changing this super Gaussian order. I'll put in some group delay dispersion later, but I'll just show you first what happens if you don't. And of course, we have to make a bit of a larger spot size here. And let's put in a phase matching angle for our crystal. So again, type 1. And the only thing that we have to take care of now is to put our seed pulse on the correct axis. So this is roughly set up as an optical parametric amplifier. You can see not too much is happening at the moment because it's a very thin crystal, but you can already see this much bandwidth passing through 100 microns of BBO. The pulse comes out pretty distorted already, and you can see the pulse shape. Like this scalloping is just some moire pattern, just because I have a fairly coarse time step here. If I change this to something smaller, like 0.4, you can see that pattern will change. Maybe I'll just leave it at 0.4. It's good enough. So this is our pump pulse of our OPA. This is our seed pulse of our OPA. I mean, it's already gone through 100 microns. So really at the beginning, we're setting in a very short seed together with a fairly long pump. If we let this go through a bit more propagation length, even 1.5 millimeters, you can see that there will be some transfer of energy, but it's going to turn into a bit of a messy thing because everything is collinear in this OPA. So my signal and my idler of my OPA, if you know how OPA works, they're all overlapping with each other, and you can see it's very heavily saturated. I've dug a big hole in the middle of my pump pulse where I've transferred the energy to the seed. So the first thing that I'm going to do is introduce a little bit of an angle. And I will introduce this angle in the pump pulse, which is convenient for reasons I'll show later. So what happens if we introduce an angle here? You can see it takes a little bit of time to run. Our light isn't as saturated, or our amplification process isn't as saturated as it was before, but you can see we're still digging a pretty deep hole here. And in the K space, you can see there's a lot of stuff which is showing up. The stuff that's in the center, this is our amplified seed. And up here, you'll see there's another very bright spot. This is our idler. So by introducing this angle between the pump and the seed of our OPA, we give the idler also an angle in K space, which is going to be useful for separating them later. And all of these other spots, these are higher order combinations of signal and idler. In the far field, this would show up as kind of a rainbow, as this OPA is very heavily saturated. But it's only heavily saturated in one little spot here. You can see, like, we've done a good job of taking energy out of our pump pulse, but only in a very small window of time. And that's because it's a parametric amplifier. It only transfers energy from the pump to the signal when they actually overlap in time. So in order to make them overlap a little bit better in time, what we can do is we can take this pulse and stretch it in time. So we do that with group delay dispersion. We can give it a good 500 femtosecond squared. And if we run that, you can see what we're going to do is we're going to stretch that pulse out, right? It's longer. The hole we're making isn't as deep, but it's wider. So in terms of the efficiency of our amplifier, it got a bit better, and we could probably even go a little bit longer to like 600. So now let's look at our spectrum in the region of interest, which in this case is from 100 to 200 terahertz. And you can see what we're doing is we are taking energy away from our pump pulse. And, well, for example, if we look at what the initial condition is, just look at this scale. So the maximum amplitude after amplification is 1.2 times 10 to the minus 5, so about 12 microjoules per terahertz. At the beginning of the crystal is a much broader spectrum. We have gain narrowing, but it was orders of magnitude weaker. So our little amplifier is doing its job and transferring some energy to the to the signal here. If we wanted to do the next step, I like very short pulses. So I want more bandwidth than this amplifier is able to give me. I mean, the first thing that I can do is I can try to tune its phase matching angle a little bit. You can see how the spectrum is going to evolve as we change our phase matching angle. Like it's a little bit better there, but getting a little bit of a hole in the middle, but that's fine for us. And you can see our whole amplification process is a little bit more efficient now. But what can we do about this blue side? What we did in the lab is to actually put a second crystal with a different phase matching condition. And this is where we can start using this sequence to good effect. So what the sequence mode allows us to do is to, well, make a sequence of events. And the first one in the sequence of events that we're going to want is a copy of this crystal. So if you click this camera button, it basically gives you a snapshot of the nonlinear crystal that you have programmed into the interface here. And then the next crystal that comes along will, well, we could, for example, use this twin button and give us a plasma crystal, but we can actually simplify things even more by taking nonlinear. So this is our crystal. It's still going to be BBO, and we're going to maybe want to adjust our phase matching angles. And we'll use a 1 millimeter thick crystal. And so this is our second crystal in our sequence. And what we can do now is we can adjust the phase matching angles of our second crystal in this sequence of crystals. So what we're going to want to do is put in the phase matching conditions for a type 2 BBO. So we would want maybe 29.5 here, and it's important to set the phi of the BBO to 0. What the simulation is going to do is it's going to run the same simulation that we ran before, but it's going to take this result, this electric field which comes out, and it's going to feed it into a second crystal. So that's what's going to happen here. So if we run this, it's just going to march its way through, run one crystal then another, and if you look at the spectrum here, you can see we've actually added some bandwidth on the blue side. And if we tune around this angle a little bit, we can decide, where our blue edge of the spectrum is going to sit and do some reshaping of the overall shape of the spectrum. And we can just sort of do this iteratively, changing the shape of our spectrum. And now this is a good point at which we can start using some of these batch modes to try to optimize our OPA a little bit. An important one is the delay between the pump and the seed of our parametric amplifier. So what this lets us do is change the relative timing. You can see this region of time in the pump pulse that we've depleted here isn't quite centered. So we're maybe leaving some energy on the table. So what we can do is we can just scan delay in a certain range. Let's give it a decent range from like -300 to +300 femtoseconds. We'll do it in 7 steps. And now you can see it's going to take a while because it has to do quite a lot of propagating through crystals on a big grid. You can see with a very large time delay, not too much is happening as we watch our other results come in. Negative delay seems to be the bad direction, but or at least it was going too much in that direction. But now the pulse is coming in, we're bringing them into overlap, and the better our overlap is, the more energy we are transferring to our pulse. And we'll use this slider in the end once the results are done to have a look at how these things are changing. So first thing I'll do is I'll set a fixed limit so it's easier to compare things. And you can see how our OPA amplitude and spectrum would change as we were to modify the timing of the pump pulse relative to the seed and this OPA. So we would probably want it somewhere here, which is maybe at a slightly positive delay, positive 100 femtoseconds, let's just say, is we're not being super careful about optimizing our laser at this point. So that's our 100 femtosecond delay. But this spectrum isn't really an accurate representation of the amplified spectrum because it includes the superposition of the idler and the signal together, which in this configuration, because we're amplifying 2 micron light with a 1 micron laser, it's in degeneracy. So idler and signal have the same spectral range. So what we can do is we can apply an aperture to the light. And we'll put this aperture in the far field. And so to know what all of these inputs of these functions are, you have to look in the documentation. But in this case, we're only interested in the first one, which is the opening angle of this aperture. And what we want to do is we want to make this opening angle small enough that it's going to filter out our pump light. So we're just going to have an aperture in our beam which will only let the signal through and block everything else. And that's going to be the last step of our little sequence here. And once it runs through, you'll see what it's going to do. It's going to kill all of the extra K space and leave me with just the amplified signal. You can see it has a nicer wavefront associated with it. It's still a saturated OPA, so it has a bit of a funny wavefront on it, but its spectrum looks more like you would get in the lab. And yeah, on the pump axis, there's just a little bit of garbage left over that managed to make it in the on-axis direction, which is probably mostly like third harmonic of the signal. So that's our optical parametric amplifier. We have amplified our signal beam by a few orders of magnitude and stuck together 2 separate crystals in order to improve its bandwidth. And at the end, we applied an aperture just to select the light that we want. All right, and that is it for this tutorial. So we learned how to set up some simple calculations, how to use some batches, how to make a simple sequence. And I hope that that's enough for you to get started. Like the name of the software is Lightwave Explorer, and the point is that you get a lot of visual feedback and you can start playing with these things. So don't be afraid to just put in numbers, put in batches, and see how some personally relevant systems of nonlinear optics respond to changing their parameters. If people like this format, I can make some more tutorials. I might do it anyway just because, well, I had COVID, so I couldn't leave my apartment for a while, so it seemed like a good thing to do. I could talk a little bit more about the underlying nonlinear optics, talk a little bit more about coding, how to actually run this kind of stuff on a GPU, some more specific tutorials, such as if you want to add a material. There's a lot more advanced stuff you can do with the sequences. I could talk about that. And there's also this whole mode for doing numerical optimization of the results. So there's a lot of stuff that we can cover, and hopefully I will someday. That's it for now. Take care and goodbye.